Hello everyone, my name is Jacob,
And my name is Andy.
and we will introduce you to the Jandy processor. So we upheld the totally original idea of naming our processor after our own names, Jacob and Andy, so that's why it's called Jandy. Our processor is based upon the MIPS architecture, and many of the properties of our processor do incorporate MIPS. So things like RISC-reduced instruction set computer, it does very simple instructions and allows for fewer clocks per instruction as opposed to your CECS processors, which have very complex instructions. They can do an instruction in one go, but usually it takes a long time. We do have fixed instruction sizes, 32-bit instructions, and we'll go over the formatting of that later. As I said, simpler instructions, we just have add, load, store, design, and just logical operations. And our CPU does implement a Harvard architecture memory. So what that means is that we have separate memory storage and pathways for instructions and data. For our instruction memory, it is read-only. It is only meant to be fetch instructions and be decoded, while our data memory is be able to be read and written too. And the advantage of doing a Harvard architecture is that the CPU can access two memory buses at once. Alright, so we do have a lot of registers that we implemented within our CPU for the multi-stage segment pipelining, but the important ones to know are our 32 by 32 register file, where we have 32 integer registers that we label them as general purpose registers, or GPRs. The important ones to note are the ones that we have a specific purpose for. R0 is meant to be just a constant of 32-bit zeros. R29 is our stack pointer, where we will use it for our interrupts when we access memory, and our return address is when we load back the original program after our interrupt service routine. We do have our program counter register itself, which will go through our instruction memory and fetch all of our instructions that we need to do. And last but not least, we have our flags registers, where we will use them for things like conditional branches. A little bit about our memory architecture. It is a 1K by 32. All of our memory space is all 32-bit and is byte addressable. There's 4 bytes right here, 8 bits in 1 byte, so 1, 2, 3, 4. We did it in big endian format, which means that the most significant bits of our data are loaded into the lowest byte of the memory address. And in order to access this data, we use an effective address line of 2 to the 12 size. You might ask, well, 2 to the 12, that's 4K, but why is your memory only 1K? And the reason why is because the way we formatted our memory is that it is byte addressable. And because there's 4 bytes within our memory location, it actually multiplies the memory we can access by 4. And so that's why you need 2 to the 12 effective address lines size.
So is your processor only capable of addressing 2 to the 12th?
No.
No, it is not.
It's only for verification purposes.
Yes.
Yeah.
The data types we do support in our processor are 32-bit signed integer. There's a total of 2 to the 32 values, and when it comes to signed integers, it is important to note that the most significant bit, the 32nd bit, is the one that determines the sign. So that is why when you look at here, the highest number is 7FFF. You'll realize that the most significant bit here is 0, because that is the highest positive number you can reach for a signed integer. And for unsigned integer, it goes from 0 to 2 to the third to the minus 1. And from 0 to FFF. So our processor also supports these kinds of addressing modes. We learned in class that addressing modes is a specification for generating an address of an operand at runtime. So operands of our RGA processor are stored in registers, both in CPU and memory. And it's important to note that the term registers can be applied to memory because memory is just a collection of registers. And so our implementation of addressing modes is as follows. We have immediate, register, and register indirect. So the first one I mentioned was immediate. In the immediate mode, the operand itself, either 16 bits for logical and arithmetic operations or 26 bits for things like jump, is part of the instruction. This addressing mode is useful, especially in specifying jump addresses, as well as data constants. So for Louis and Ori, we use those for logical operations where we load the upper 16 bits with 1, 2, 3, 4 right into R1, and at the same time I order the same register with the lower 16 bits of 9876. And as well as doing an add immediate instruction where I still use the same kind of addressing mode, the immediate, where I add R1, which we have right here, with the constant of 3, and that results in the result being loaded into R2. Now, and the last thing, the 26 bits that I mentioned, we use that for jump right here. So it's the jump constant is 2. However, when we execute the instruction, the PC is loaded as 8. And the reason why is because we basically shifted left and essentially concatenate it with 2-bit 0 at the end. So that multiplies it into 8. And we keep the 4 most significant bits of the program counter as we load. Next, we have register mode, where we're directly accessing data from a register. And you can see here, when the R1 and R2 from the last example, we just access those directly and load them into R3, and that results in that. And we use these kinds of addressing modes when it comes to arithmetic operations like add, subtract, or logical operations like shift right and shift left. And our last addressing mode is register indirect. This one we use for load, store, and jump only. The two main purposes of using this kind of addressing mode in our processor, register indirect, is so that we can use it for loads and stores when we calculate an effective address for our memories, our data memory in particular, or when we use it for conditional branches and things of similar stuff. So we see here, we did do an offset of 1 just as a for simulation purposes. We have our effective address right here. However, as I mentioned in our Harvard architecture, we only need to use the last 12 bits of our result, which is 0F0 of this result right here, and we use it to execute this instruction store word, where we store our result into memory. And the same thing applies to load word, where we use the same effective address and load it back into another register. And last but not least, we have our instruction set and binary format of our processor. Instructions define what operations and addressing mode our processor executes. So we do have 32-bit wide instructions, and that's the only size we have. We learned in class a very important rule: simplicity favors regularity. You want to keep it all consistent so that the architecture is not too complex to construct. We have 3 types. R-type is the first one. We define R-type as the first 6 bits to be all zeros. We have 2 source operands, RSRD, and 1 destination operand, RD. These are R-types we mainly use for arithmetic and logical operations, as I mentioned: add, subtract, shift right, shift left, and all the logicals like and, or. And the function code, the last 6 bits are what decides which logical or arithmetic operation to execute. Our second is I-type. The I-type, it has one base or source operand. The reason why I say source and base is because sometimes we will use I-types for loads words and store words where we have an offset to our base effective address and we do an add to it. The 16-bit immediate value right here is what really defines the binary format of our I-type. And as I mentioned, there's two main reasons for the logical and arithmetic operations where we do add immediates, subtract immediates, or to do a base offset for addressing memory. And the third type is the J-type. These are defined with the 6-bit opcodes. There's jump and jump at length, and there's just the 26-bit jump address where we will use to calculate the address to which the program will jump to. And the register that gets loaded is our program counter, which will then decide which instruction to fetch next within the instruction memory. Lecture break.
Now we'll talk about the hardware design of our GND processor. And these are basically just the hardware design block diagrams right here. We're going to zoom into this one. The CPU test is the top level wrapper module of our GND processor. It instantiates the CPU module and the data and the I/O memory modules. And inside the instruction unit, there's also the instruction memory module. The purpose of the instruction unit is to fetch the instructions and then it forwards it to the MCU, the MIPS control unit, which decodes, and then in the MCU it generates all the control words for the instruction unit and also the integer data path as shown here. So the MCU also generates the control words for the data memory chip select, read, write, as well as the I/O chip select, read, and write. And the difference between our processor and the baseline is that we implemented an I/O memory module, which also has the interrupt request as well as the interrupt acknowledge. And this is the instruction unit module. So all these bits are controlled in the MCU. The PC select is the line that selects which PC to load if PC load is asserted. And if PC select is 0, then it would have the branch address. If its PC select is 1, it would have the jump address. And if PC select is 2, it would come from the LU, and we'll talk about that later when we load the PC. And PC increment is just to increment the program counter every time we finish an instruction, as well as there's also a wire PC out so that we can save the PC to a register or a memory location. The instruction memory is read only, so the IM write signal is tied to 0, and we control the IM check select and the IM read, and as well as the IR load in the MCU when we want to load a new instruction in the instruction register. And it will come out to a wire to control all the signals in the integer data path, as well as sound extending the last 16 bits if we need it for the I-type instructions. So this is the integer data path module. As we were talking about the sound extended 16, it would be tied to this DT right here. And the IR 25 to 21 would be the S address. The IR 15 to 11 would be the T address, and then the IR 20 to 16 is the T address, and then the 15 to 10 is the D address. So all the input signals are controlled in the MCU as well. So the D enable, it enables you to write to the register file at the D address, which is controlled by a deselect mux. And if the deselect is 0, then it would just normally write to the D address. This is used for R-type instructions. If the deselect is a 1, then it would write to the T address, which is for immediate instructions, I-type instructions. And for, if its deselect is 2, that would be the return address. That's our first iteration of the interrupt, we would use that. And then the stack pointer is, the deselect is 3. The difference between the baseline and ours is that we added a S address mux right here so that we can access the stack pointer so that we can further use the interrupt request and the return from interrupt, which I'll talk about later. And this T-select is just for the immediate operands as well as the operands that come from the R types. And high-low loads registers are used for the division and multiplication operations, and it is only loaded when this high-low load signal is asserted. And this DY comes from the data memory or the IO memory, and we'll show that later. And all the load and the store words, the effective addresses of them are calculated through the ALU, and it is fed right here. And I'll show to the next slide. Right here. So when we want to write to a memory location, we load it through RT and we feed it through here. And we added a DM select, and this is so that we can write to the stack as well as the memory locations. DM select 0 would just write whatever is in RT to the data memory at that address. If DM select is a 1, then it would write the flags to the memory address at the stack pointer, which I'll show later. And then the same goes for the PCN.
Are those flags in your control unit or are they in the data path module?
They're from the control unit, but we simplified it.
Did you re-register them there or?
Yeah, you re-registered them.
You re-registered?
Yeah, yes.
Okay.
And this is the whole CPU, showing all the interconnections between the 3 modules. So for our first enhancement is the barrel shifter, which is done within the ALU. And it is just, the ALUs consisted of the multiply 32-bit, the division 32-bit, and then the normal ALU operations such as AND, subtract, or shift left, shift right. But the barrel shifter 32 is where we use the shift amount, so then we can shift a specified amount for the shift operations. And this is our diagram for it. It takes in the RT and then it takes in the shift amount. And LR select is the select line that selects the mode that it shifts. So shift right arithmetic, shift left logical, or shift right logical. And the Y is just the output of the shift, barrel shifter. So in this instruction, we don't use RS. We use RT as the source register, and then we look at the shift amount so that we can shift the specified amount. And basically the LR select is controlled by the MCU, so whatever the function select is, it will control the LR select appropriately to the correct mode. And it'll store the result in RD. And this is our second enhancement. It's the interrupt service routine. So before, the interrupt service routine would save the program counter to the return address, and then to return from the interrupt, we would just use the jump register to the return address. But for our enhancement, this is basically the RTL. We would use a pre-decrement push to the stack. So we would pre-decrement the stack pointer, and then we would push the program counter to the stack. And then we pre-dec it again, and then we would push the flags onto the stack. And then that's where we can change the program counter to the very first stack pointer, and then we would put interrupt acknowledge as 1. And this is all the steps that we took for implementing this.
Andy, how did that memory 3FC, where's the path to get that on your, that's the fifth step, right?
Yeah.
And so where did that get loaded? To
That
be
got
able to
loaded-
write it in the fifth step?
Yeah, that got loaded in,
So you've got 4 steps in front of it.
yeah,
At what point did you actually read memory location 3FC? So you wrote to memory twice. When did you read memory?
we didn't actually read the stack pointer location, we used the stack
Used the
pointer
ALU.
init. Yeah, the ALU to generate the stack pointer init.
Would have been good just to show that RTL steps that are kind of maybe going in parallel with the other 4 steps.
Yeah,
Because you can't just pull that out of a hat,
Yeah.
so to speak.
that's one thing we'll fix.
Well, it's just in the presentation, I'm
Yeah.
sure it worked okay. Yeah.
And this is the return from interrupt request. It's a post decrement pop, so we would pop the memory at the stack pointer back onto the flags, and then we would increment the stack pointer, and then we would pop the program counter back, the memory at the stack pointer back onto the program counter, and we would increment the stack pointer. And this is how it's done.
Yeah.
Yeah.
Good.
Yeah.
And this is where, sorry, I didn't talk about earlier, but this is where we would use the DM select to write to the flag, and yeah, and to write back to the stack pointer, we would just go through the ALU and increment and decrement. And this is another enhancement, is the input instruction for the I/O memory modules. It's basically the same step as a load word, but we would utilize the I/O memory module, and it's the same exact step. We just fetch the instruction, decode, and then we would calculate the effective address of the I/O memory module, and then we would store the data at the I/O memory module and store it to DN, and then we would finally write it to the register right here. Here's an example. So input R6, and then the offset is 0 for simplicity's sake, and R2 is the base register. The base register is 0C0. That means the effective address is 0C0, and that whatever's at 0C0 we would write back into R6. No, sorry. This is oh yeah, sorry. Okay. So it's byte adjustable, so 0C0 would be, it would have 80007FFF written to R6. And then the same goes for R9. And this is our other enhancement, the output. It takes the same steps as the store word, in which it stores the register indicated by RT into the I/O memory module pointed to by the effective address, by the base address and the offset. So we calculate the effective address, and we would just go write back I/O, and we would write the data at RT back into the I/O memory right here. And this module is to verify all 4 enhancements. So we put an interrupt request right here, right after the load immediate R5, 5A, 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 5A. And as you can see, we would write R1, the data R1 through R5 right here, and then we would get the interrupt request. This is when we would push the program counter onto the stack pointer, the memory at the stack pointer onto the program counter, and then we pre-decrement the stack pointer, and then we would store the current program counter onto the stack pointer, and then pre-decrement again, and then push the flags right onto the stack again. And right after it are these instructions. We would load R16 with 100100C0, R17 with 80000 FFFF, and R18 with hex 10. And that means we would go through a loop 16 times, in which we would use the output function and output the whatever's in R17 onto the IO memory. And then each time we go through the loop, this is the loop right here, we would shift right arithmetically twice. So that means that it'll keep the sign bit and it'll shift twice. So then the next one would be E003FFF, and it'll go on. And then add immediate 4 would increment the memory pointer by 4. So then we can push on to the next 32 bits of memory, IO memory. And then the add immediate R18 would decrement the counter by 1. So then that means we go through the loop 16 times until R18 reaches 0. And this verifies all the outputs.
Okay, so the enhanced instructions that we wanted to do but didn't get around to in time these are just a few examples of them. You may notice that a very similar one is add 3. This was an idea of ours that we actually wanted to do. Decrement jump not 0. This one we could just check the flags and jump to an effective address, jump register and link, and clear. We have a set interrupt enable, but I don't think we have a clear interrupt enable. Usually we just kind of set that after in one of the states. And the reason why I have this little instruction format down here with the E key is that I wanted to explain how we would do our add 3 in the future. So normally the bits 10 to 6 over here would be used for a shift amount for any of the logical shifts. However, in our E key format, we would actually use this as our third source operand. We would keep this as our destination register just for the sake of consistency. However, if we were to modify our integer data path in order to be able to execute add 3, there's a bunch of ways to do it. You can extend a few muxes, you can add some more muxes, but in the end, I would take the result of the ALU of the first 2 operands, feed it back into one of the inputs, and the second input to our ALU would be our third source operand, do another addition, and that would be our result. So just a few closing remarks. Andy and I we did find this class very fun. Even though it was difficult at times, we did find that we found a lot of insight into computer engineering design. Just one more thing I'd like to add is that I noticed that the culture does like to attribute a lot of credit to designing the system, but I think nowadays we have to also emphasize on verification, and that's the whole purpose of our assignments is to do, because verification is starting to grow now, and people want to look for students like us to be able to look for the details. So as a wise professor once said, the devil is in the details.
Right.
Thank you.
Okay, excellent. Thank you.